We operate under a really comforting, very common belief that adding more connections to a system creates stability. We build redundant pathways in our networks, we interconnect our power grids, and we intertwine our financial institutions. It's all built on this assumption that a web is inherently stronger than a single thread. But in this explainer, we're going to see exactly why that fundamental assumption is flawed. The reality is that very connection is the exact mechanism of collapse. There's a hidden structural force at play in our most vital architectures, one that silently transforms local safety into global catastrophe.
What we're actually looking at is a really stark contradiction. Local optimization on one hand, leading directly to global collapse on the other. And the immediate consequence of this is deeply unsettling. The very systems we rely on every single day are specifically designed to route around local damage. Yet by doing exactly that, they mathematically guarantee their own total failure. To understand how a system successfully destroys itself, we have to stop looking at the symptoms and instead examine the structure itself.
To ground this, let's visualize a persistent physical system. Picture a heavy steel grate suspended high in the air. It's held up by a series of identical vertical metal rods, and each one is bearing a massive, perfectly distributed hanging weight. The whole system is in perfect tension. The rods are completely static, just humming with stored kinetic energy. Now, we aren't going to assign any specific meaning to this lattice just yet. Just observe the physical baseline here. It's stable, it's interconnected, and it's under immense, invisible strain.
Now, watch the physical reaction. A single rod snaps. It breaks under some minor, localized defect. Instantly, the physical tension doesn't just disappear, right? It redistributes. The heavy weight that was supported by that broken rod immediately transfers its downward force to the neighboring, surviving metal rods. The system is simply obeying the laws of physics, attempting to carry the load through its remaining connections.
Let's step away from the physical metal for a moment and look at digital infrastructure. In computer networks, like the internet, when a single node or router fails, the system performs a perfectly rational localized optimization. It shifts the traffic elsewhere. It simply routes around the damage. We consider this a feature, right? Not a bug. It's the system doing exactly what it was programmed to do to ensure survival.
To put that into perspective, think back to December 2012. 40% of the global Gmail service vanished entirely for 18 minutes. And it wasn't some massive cyber attack. It was a routine update to load balancing software that contained a tiny logic error. A single node went down, and the system did what it always does. It sought an alternative path. But here's the crucial point. What happens next? These redundant network systems quickly route that massive wave of traffic through alternative, longer paths. But those secondary backbones and the nodes along them, well, they're mathematically unprepared for that sudden, immense volume of data. The traffic from the failed nodes surges into the healthy nodes, and it immediately overwhelms their processing capacity.
As a result, useful communication simply halts. The nodes don't necessarily power off, but they become completely paralyzed. The routes remain technically valid, sure, but they are entirely dysfunctional. It creates what we call a walking failure, a silent ripple that just moves right through the network. Sections go down, pass their load to the next section, crash it, and move in this continuous wave of localized optimizations that end up paralyzing the global network.
Now, let's take that exact same structural behavior and apply it to power transmission networks. When a single electrical transformer fails or is taken offline, shifting loads to nearby elements is the expected, perfectly correct local behavior. High-voltage systems are literally designed so that if a line drops, the electricity instantly seeks the path of least resistance through the remaining grid. The goal is simple: keep the lights on.
But here is where the constraint really tightens. The load transfers instantly, and this surge current automatically pushes neighboring electrical nodes, which might already be fully loaded or even slightly overloaded, way beyond their physical capacity. So the system is desperately trying to save itself, but by shifting the burden, it transforms a single point of failure into a sudden, massive spike across multiple healthy nodes.
And the physical limitation here is absolute. You might be wondering, why not just isolate the failing grid? Well, because the control signal meant to warn the system and disconnect the parts moves at the exact same speed as the electrical power itself. The warning literally cannot outrun the overload. The propagation of failure is moving at the speed of light. The system is completely trapped by its own physical interconnectedness.
Let's go back to our physical lattice. Under that sudden, transferred weight from the first broken support, the adjacent rod snaps. It lets out a sharp crack.
It physically parallels the digital data surges and the electrical overloads we just looked at. The surviving rods are now taking on totally unbearable weight. The local failure is successfully spreading.
We can see this exact same pattern in financial networks, where the stakes are entire global economies. Institutions rely incredibly heavily on the cross-ownership of debt and equity. It's designed to act as a shock absorber against isolated losses. The theory goes that if one bank takes a hit, the loss is safely diluted across the massive, interconnected web of the global financial system.
But there's a really dangerous hidden trap here. Risk sharing quickly becomes risk spreading. Beyond a certain density of connections, a critical tipping point, the exact mechanisms built to dilute local distress automatically amplify it globally. The financial interconnections completely cease to be a shock absorber. Instead, they become a shock amplifier. The connectivity itself engenders fragility.
Let's look at the mechanical reality. When firm A holds the debt of firm B, their asset equations are inextricably linked. A local default by one firm mathematically forces the asset values of interconnected firms downward in a continuous chain. If you actually try to calculate the recovery value at maturity, you find a nonlinear equation system where the falling value of one firm automatically and inevitably pulls down the value of the next. We've reached the climax of this structural tension. Whether we're looking at internet routing protocols, high-voltage power grids spanning entire continents, or the incredibly complex derivatives of global finance, the behavioral pattern is undeniable, and it is completely identical. The system attempts to route around local damage, overburdens the adjacent structures, and spreads the failure.
So we can finally name this hidden structural force. It's a cascading failure. A progressive system collapse caused by positive feedback from a single failing part. When one part fails, others compensate overloading themselves, which then prompts additional failures. The very feedback loop that was meant to ensure reliability is actually the engine of the cascade.
Structural engineers describe this exact cascading motion as the zipper effect. In load-bearing structures, like the tragic Hyatt Regency walkway collapse, the loss of one discrete vertical suspension rod didn't just cause a sag. It exponentially increased the load on the next rod in sequence, tearing the structure apart linearly, exactly like a zipper opening up. And so, we bring our physical lattice to its final state. The exponential redistribution of weight shears the remaining metal rods. They snap sequentially, faster and faster, as that positive feedback loop accelerates. The tension is only finally released when the entire structure is on the floor. Nothing remains. This brings us to a phase where the window for escape closes entirely. Once that cascade threshold is crossed, once the surge current actually hits the grid, once the data floods the alternative router, once the asset values mathematically trigger default, the situation across all these complex networks becomes entirely irreversible. At this point, escape becomes mathematically impossible. The loss of alternative routes locks the system into a continuous chain reaction. Because the system is acting autonomously, based entirely on its own internal logic and physics, it cannot be halted from within. The network literally consumes itself precisely because it is connected.
Which leads us to a pretty profound reframing of how we view these disasters. When the power grid goes down, or the internet halts, or the market crashes, we usually look for the error. We try to find the villain. But the rerouting of data, the shifting of electrical load, and the transfer of physical and financial tension, those were not errors. They were perfect, flawless executions of the system's design.
And this leaves us with a final, chilling reality to take away from this explainer. The system was never failing. It was successfully following the exact physical and mathematical rules of its own structure to an inevitable conclusion. So, if connection is the mechanism of survival, we have to ask ourselves, at what point does it become the absolute guarantee of our shared collapse?